In this video, I want to give you an analogy to help you understand confidence intervals. I'm not going to actually show you how to calculate a confidence interval in a regular confidence interval problem. I will describe the process of creating a confidence interval in a regular confidence interval problem, but not in very much detail, since the main purpose of this video is to give you an analogy to help you understand confidence intervals more deeply. I want to help you understand what a confidence interval shows and why it works the way it does. The main reason why I wanted to make this video is because I think it can be easy to learn the steps of creating a confidence interval, but it can be difficult to really understand what a confidence interval really means or what it really shows. The picture on the screen is meant to be showing an island that is 160 feet long. I've marked off different locations on the island with tick marks. I'll call these tick marks the locations on the island in this video. The number under each tick mark is showing the distance between that location and the left end of the island. For example, location 10, which is at this tick mark right here, is 10 feet from the left end of the island right here. And location 20, which is at this tick mark right here, is 20 feet from the left end of the island. So each of these numbers under the number line is meant to be showing the distance between that location on the island and the left end of the island in feet. Let's say someone tells us that a helicopter was hovering above a certain location on this island for an entire year. The person tells us that during that year, the helicopter hovered above one of the locations, meaning one of the tick marks, and then disappeared. The person also tells us that the helicopter never changed its location during that entire year. That means that the helicopter hovered above one tick mark for the entire year and then disappeared. Let's say that we're interested in figuring out the location that the helicopter was hovering above during that year, but the person who told us that the helicopter was hovering above the island also tells us that they don't know the location that the helicopter was hovering above. We decide to go to the island to look for evidence to help us figure out the helicopter's location during that year. We search the island and we find a small piece of the helicopter at a certain location on the island. Let's say we find a bolt that fell from the helicopter, and we find that bolt at location 110. So we find a bolt laying on the ground on the island at location 110, and we can tell that this bolt fell from the helicopter. I'm not very good at drawing a bolt, but I'll try my best. We want to use this bolt to help us figure out the location that the helicopter was hovering above during the year that it was above the island. But before we talk about using the bolt to help us figure out the helicopter's location, let's talk about what happens when you calculate a confidence interval in a real confidence interval problem. In a basic confidence interval problem, you're told that a sample was recruited from a population and that data was collected from the sample. What this often means is that a researcher was interested in learning something about a large group of people, so the researcher recruited a group of volunteers from that large group of people and collected information from that small group of volunteers, maybe with a survey. And the population that's mentioned in a confidence interval problem it doesn't even have to be a group of people, but it's often a group of people. But if it is a group of people, it doesn't have to be a group of people that are all living at the same location. A population of people is just a complete group of people in which the members have something in common with each other. When a person thinks about a population, they often think about a population like the population of California, which is a group of people that all live in the same place. But a population just has to be a complete group of people in which the members have something in common with each other. The population of California would be a population because the members do have something in common with each other. They all live at the same place. But the group of people who own laptops, when you think about all people who own laptops in the world, that's also a population because it's a complete group of people in which the members have something in common with each other. Also, all cell phone users would be a population of people because they all have something in common with each other. Let's say that you're working on a confidence interval problem, and the confidence interval problem says that a researcher is interested in a population of students that all attend a certain university. The question usually won't tell you the number of people in the population, but let's say that there's 20,000 students in that university population. The problem might say that a researcher recruits 1,000 students from that university population of 20,000 students, and that the researcher then collects data or information from each of those 1,000 students, maybe with a survey. Those 1,000 students that the researcher collected information from would be called a sample of the population of 20,000 students, because the 1,000 students are just a piece of the entire population of 20,000 students that attend that university. The problem will also say that a certain population value, which is called a population parameter, that's a technical word, is unknown, and that the researcher is going to use the data collected from the sample to calculate a sample value called the sample statistic, and that sample statistic will be used to estimate the population parameter. I'll give you an example that takes out those technical words. The problem might say that the mean height of that population of students at that university is unknown, and that the researcher is going to use his or her data set to calculate the mean height of the sample of students that the researcher recruited, and the mean of the sample will be used to estimate the unknown mean height of the entire population. What this means is that the entire population of 20,000 students does have a mean or average height, because if you did record the height of all 20,000 students and you added up those 20,000 heights and divided the total by 20,000, you would get a number, and that number would be the mean height of that population. But the researcher in the problem isn't able to record the heights of all 20,000 students, maybe because the person doesn't have enough time. So the person has instead recorded heights from the 1,000 people in their recruited sample, and the researcher has or is going to calculate the mean height of those 1,000 students in the sample, because the mean height of those 1,000 students in the sample can be used to at least get a rough idea or an estimate of what the unknown population mean equals. The idea behind, well, first, I think I might have said this already, but the mean height of the entire population of 20,000 students would be called a population parameter, because it's the mean of an entire population. It's a value that describes an entire population, and the mean height of the 1,000 students in the researcher's recruited sample would be called a sample statistic. A sample statistic is just a value that describes a recruited sample and not the entire population. So the mean height of a sample of people would be called a sample statistic. The idea behind using a sample statistic to estimate a population parameter is that even though the sample statistic is not necessarily the same number as the population parameter, the population parameter should be at least somewhere close to the sample statistic, especially if the sample was recruited randomly from the population. So if you randomly recruit 1,000 students from a population of 20,000 students at a university, and then you calculate the mean height of those 1,000 students, that sample statistic, or that sample mean, should be at least somewhere close to it should have a good chance of at least being somewhere close to the mean height of the entire population, which is the population parameter. There is a chance that it could be far away from the population parameter, but it's less likely. And so the logic behind using a sample statistic to estimate the unknown population parameter is that even though the sample statistic isn't going to give you the exact population parameter, it's not going to be the exact same number, it at least should give you a rough idea of what the population parameter equals. What you actually do in this type of confidence interval problem is you take the sample statistic, which is often provided to you in the problem, and you add and subtract a value called the margin of error. And the margin of error is usually something that you have to calculate in that problem. It's not usually given to you. And adding and subtracting the margin of error, adding the margin of error to the sample statistic, and subtracting the margin of error from the sample statistic gives you two values called a lower limit and an upper limit, and the interval or span of numbers between the lower and upper limits is called the confidence interval. So after you've calculated the lower limit and the upper limit, you've created a confidence interval, because the confidence interval is just the interval of numbers between the lower and upper limit. After you create the confidence interval, you can say with a certain amount of confidence that the population parameter falls somewhere inside of the confidence interval that you created. For example, you might say that I'm 90% confident that the population parameter, the unknown population parameter, falls somewhere in the confidence interval that I created. So in my analogy, we can say that the entire helicopter that was hovering above the island is the population, and that the bolt is a sample of the helicopter. We can say this because the bolt is a piece of the helicopter, or at least it used to be a piece of the helicopter. Also, the helicopter is the complete thing that we're interested in learning about, and the bolt is just the piece of that thing that we're using to help us gather information. So the unknown population parameter or population value that we're interested in is the location above which the helicopter was hovering during that year. And the sample statistic that we're using to estimate that population parameter is the location of our sample, which is the bolt that we found on the ground. So our sample statistic is 110, because 110 is the value, the location value that goes along with our sample. And this sample statistic is going to be used to estimate the unknown population parameter, which is the location of the helicopter, or the previous location of the helicopter that this bolt came from. So how can we use the location of our bolt, which is our sample statistic, to estimate the unknown population parameter that we're interested in, which is the previous location of the helicopter? We might be tempted to think that the bolt must have fallen straight down from the helicopter. So since we found the bolt at location 110, the helicopter must have been hovering above location 110. You might be tempted to think that the sample statistic and the population parameter must be the same number. The problem is that this isn't necessarily true. A sample statistic and a population parameter don't have to necessarily be the same number. If you recruit a sample of 1,000 students from a university population of 20,000 students, and you calculate the mean height of the 20,000 students, and you calculate the mean height of the 1,000 students that you measured, the mean height of the 1,000 students won't necessarily be the same number as the mean height of the entire population of 20,000 students. The sample statistic won't necessarily line up with the population parameter, but the sample statistic will often be close to the population parameter. So in this example, the wind might have carried the bolt a certain distance away from the helicopter. But if we assume that the wind is only so powerful on this island on most days during the year, then we could assume that the bolt must have only traveled a certain distance away from the helicopter. So if we assume that the winds are only so powerful and that the bolt would have been likely to only travel a small distance away from the helicopter, then we can assume with a certain amount of confidence that the helicopter's location should be somewhere close to the location that we found the bolt at. We could say with a certain amount of confidence that the helicopter's location should be at least somewhere in this area around 110, around here. And we could justify this conclusion by saying that if the bolt was outside of this area, then it would have had to, then the bolt would have had to travel a distance longer than it would have been likely to travel. The problem is, if we wanted to mark off a boundary somewhere over here and mark off a boundary the same distance to the right of the bolt over here to make a conclusion that the helicopter's location should have been between those 2 points, how do we know how wide that interval should be? Well, in order to know how wide that interval should be, we have to have an idea of how powerful the winds are on this island. Let's say we read about the wind patterns on this island, and we find out that on 95% of the days during the year, the wind would only be powerful enough to carry the bolt 10 feet or less away from the helicopter. So then we think, okay, as long as the bolt fell on one of those days during the year, then we would know that the bolt did not travel more than 10 feet away from the helicopter. So let me put that on the screen up here. We find out that on 95% of days during the year, the wind would, on this island, would only be powerful enough to carry the bolt 10 feet from, or less, from the helicopter. And how many days would that be? Well, to find out, we would have to multiply. We would have to turn 95% to a decimal and multiply 0.95 times 365, since there's 365 days during the year. (365) times 0.95. Well, it doesn't come out to an even number, actually, but for this example, we'll just round it off. We'll round it up to 347, even though that's not exactly 95%. So we find out that on 347 days during the year, the bolt would travel 10 feet or less from the helicopter, because on those days the wind would only be powerful enough to carry the bolt 10 feet or less. And even though this number isn't exactly 95%, for this video we'll just say that it is 95%, just to make things more clear or easier to explain. So what can we do now? Well, we know that if the bolt happened to fall on one of these days, on one of these 347 days during the year, then the helicopter would have to be somewhere within 10 feet of location 110, because if the bolt did fall on one of these days during that year, on one of these 347 days, then the wind would only be powerful enough to carry the bolt 10 feet or less from the helicopter. And if that's the case, and if the bolt did fall on one of those days, then there wouldn't be any way that the helicopter's location could be more than 10 feet away from 110. So maybe we could add and subtract 10 from this number 110, like this. And we can make 100 our lower boundary, of the interval we're creating. And we could make 120 the upper boundary. So 100 is the lower boundary and 120 is the upper boundary. This distance of 10 right here and this distance of 10 over here would be called our margin of error. And the entire interval between 100 and 120 would be our confidence interval. If we decided to use 10 as our margin of error and to create this confidence interval between 100 and 120, then our conclusion would be, we believe with a certain amount of confidence that the helicopter's location would have been somewhere between 110 and 120, because even though it's possible that the helicopter's location could have been to the left of 100 or to the right of 120, in order for that to be true, it would mean that the bolt would have had to have traveled a distance longer than it would have been likely to travel on most days during the year. But if we conclude that we believe that the bolt if we conclude that the helicopter should have been somewhere between 100 and 120, if we conclude that the unknown population parameter, which is the previous location of our helicopter, should have been between 100 and 120, how much confidence can we have in making that conclusion? Well, we're assuming that if we make the conclusion that if we make the conclusion that the helicopter's location was somewhere between 100 and 120, it means that we're assuming that the bolt fell on one of these 347 days during the year, and that it didn't fall on one of the other days on which the wind would have been powerful enough to carry the bolt more than 10 feet from the helicopter. Because if the bolt, let's see how many days during the year that would be. 365 minus 347 would be 18. If the bolt did fall on one of these 18 days on which the wind would have been powerful enough to carry the bolt more than 10 feet, then the helicopter would be outside of the helicopter's previous location would be somewhere outside of our confidence interval, because if the bolt did fall on one of these 18 days, then it would mean that the bolt traveled more than 10 feet from the helicopter, and that would mean that the distance between the bolt, where we found the bolt on the ground, and the helicopter's location would be longer than a 10-foot distance. If the bolt fell on one of these 18 days, the helicopter's location would be somewhere out here or somewhere out here, meaning somewhere in these areas at which the helicopter's location would be more than 10 feet from where the bolt landed over here. But if we assume that the bolt fell at random, meaning the day on which the bolt fell was completely random, if we assume that the bolt had an equal chance of falling on each of those 365 days, and it just fell randomly on a certain day, then we can say that the bolt had a 95% chance of falling on or a 95% probability of falling on one of these days in which the bolt would travel 10 feet or less. And we can say that the bolt would have had a 10% probability of falling on one of these other 18 days on which the bolt would travel more than 10 feet because of the wind being more powerful. So we know that if we know that the bolt had a 95% chance of falling on a day on which it would travel 10 feet or less, then we know that, or we can say that we're 95% confident that the bolt did actually travel 10 feet or less. Our confidence comes from that probability. If the bolt had a 95% probability of falling on a day when it would travel 10 feet or less, that pretty much means that the bolt had a 95% probability of traveling 10 feet or less. The bolt had a 5% probability of traveling more than 10 feet. And since we know that the bolt had a 95% probability of traveling 10 feet or less, we can now say afterward, after the bolt already fell, that we're 95% confident that the bolt did travel 10 feet or less. Whenever you know the probability of something happening, you can say afterward that you have that much confidence that that thing did happen. For example, if I heard that there was a coin toss sometime in the past, and I don't know whether that coin toss came out heads or tails, I know that that coin toss had a 50% probability or a 0.5 probability of turning up heads, which means I can now afterwards say that I'm 50% confident that that coin toss turned out heads. Or if I heard that there was a dice roll in the past, if I heard that a person rolled a certain piece of dice, and I don't know which side it landed on, I can say that I'm 16% confident that the dice landed on 3, because I know that the dice, or the piece of dice, had a 16% or a 0.16 probability of landing on a 3. So the probability of something happening leads to your confidence, later on leads to your confidence that that thing did happen. So we know that there was a 95% probability that the bolt would travel 10 feet or less, which means we're now 95% confident that the bolt traveled 10 feet or less. And if we're 95% confident that the bolt traveled 10 feet or less, that therefore means that we're 95% confident that the helicopter's location was somewhere within 10 feet of where we found the bolt, right here at location 110. So we would say that we are 95% confident that the helicopter's previous location was somewhere between 100 and 120 inside of our confidence interval. We know that the only way that the helicopter's location could be outside of this interval is if the bolt fell on one of these 18 days on which the bolt would be capable of traveling more than 10 feet. And we know that there's not a very good chance. We know that if the bolt fell randomly, there's not a very good chance that the bolt would have fallen on one of these 18 days, simply because this isn't a large number of days. We know that there's a much bigger chance, specifically a 95% chance, that the bolt would have fallen on one of these 347 days on which the bolt would have traveled 10 feet or less, which is why we have this pretty good amount of confidence that the helicopter's previous location, which is our population parameter, is somewhere inside of our confidence interval. And I hope this video was helpful in helping you get a sense of the logic behind confidence intervals. Thanks for watching.